this shouldn't be possible. Scientists founded an amazingly rare star and one of its kind, where its formation was of a totally different kind, showing very unusual spectral absorption patterns of elements found on the surface of it when observed through the telescope. For the first time in history, scientists found a star formed out of a rare event in the early universe. This star is one of the oldest stars in the universe, formed after the first generation of stars exploded as a supernova. Among those first-generation stars, there was a specific star called a Barbenheimer Star, which is an enormous first-generation ancient star that exploded in a way previously thought impossible, resulting in an unusual pattern of elemental ashes that has left behind a trail of evidence still visible after billions of years as stars and gas clouds. This Barbenheimer star was a highly unusual star formed 13 billion years ago and must have a mass of at least 50 solar masses. This Barbenheimer star dies as a supernova explosion, releasing all the synthesized heavy elements it created during its lifetime. The new elements are mixed together, forming into a gas cloud, where new stars are formed out of it, especially the star which we are going to talk about, which is the J0931+0038 star. This name seems too long and boring, doesn't it? Well, let's nickname this star. Before we do that, make sure to like and subscribe to learn, manage, and be pro. Let's call this star Barbenheimer Star. Whatever happened back then before the formation of the Barbenheimer Star must have been unique, rare, and amazing. Those first generational stars back then are totally different from current known stars because our current stars had gone through a general chemical evolution, which means there is a significant amount of heavy elements ranging carbon to iron. While those first generation stars back then didn't have any significant amount of heavy elements because they were the first masses of stars majorly containing only few elements like hydrogen, helium, and lithium. The Barbenheimer Star is a distant, bright red star which is 13,000 light-years away and was captured by the SDSS Milky Way Mapper program in 1999. This program observes and records the star's spectrum, measuring the star's light at different wavelengths. What's interesting is that a star's spectrum can reveal many things like the temperature of the star, color of the star, chemical composition, etc. More importantly for this video is the chemical composition of this star, and this is what intrigued the stellar archaeologists. Stellar archaeologists are astrophysicists, studying the early history of the universe, based on its early composition. Stars are formed mostly by hydrogen and helium, and the rest of the heavier elements present were created in previous generations of stars, which eventually exploded, releasing elements into the interstellar medium, space, for new generations of stars. These heavier elements show up in the star's exterior and release light energies under different wavelengths, traveling out to space, captured by the telescope, and showing measurement as peaks and valleys in the spectrum. Now you might wonder how heavy elements formed deep in the layers of a star get out to the exterior of a star. It's true that the heavy elements produced deep in a star's core indeed cannot be directly observed through spectroscopy. However, these heavy elements are eventually brought to the star's surface through various processes, allowing astronomers and stellar archaeologists to detect them in the star's spectrum. One of the various processes is, in many stars, especially during certain stages of their evolution, like red giants or during supernova events, convective mixing processes bring material from the stellar interior to the surface. This mixing can carry newly synthesized heavy elements produced in the core to the stellar surface. In some regions of a star's interior, energy is primarily transported by radiation. However, if the temperature gradient is steep enough, instability can develop, leading to the formation of convective cells. These cells consist of rising parcels of hotter material and sinking parcels of cooler material. As this material rises, it carries with it elements synthesized in the stellar core through nuclear fusion processes. Another way is through the stellar winds, which is the continuous outflow of material from the surface of a star into space. It is driven by various mechanisms, including radiation pressure on gas and dust grains, magnetic fields, and the heating of the star's outer layers. with the help of a pulsation process where the outer layers of the star expands and contract rhythmically, thereafter sheds the outer layer. During the expansion phase of a pulsation, material from the star's interior can be dredged up to the surface. As the outer layers expand, they become less dense, allowing material from deeper layers to rise due to convection or other mixing mechanisms. The Barbenheimer Star has very unusual abundance patterns of heavy elements. Here, the term heavy elements is meant by the elements heavier than helium, showcasing the broad number of atomic elements starting from carbon to neutron, capture elements like the barium, uranium, etc. Barbenheimer Star has a relatively high metallicity of iron, but it has extremely low abundances of other elements like sodium, potassium, scandium, and also extreme high abundances of strontium, yttrium, manganese, nickel, and zinc. Also, there are clear detection of molybdenum, ruthenium, and palladium. The thing is, unlike the stars today having a pattern of heavy elements based on its abundances, this star has an irregular variation of elemental abundances in between the range of atomic elements. Examples such as barium, titanium, scandium, and many others too. When analyzing the abundances pattern of the heavy elements, observed 4 remarkable features about this star which really stood out, clearly indicating the formation of this star was a very rare kind, and till to this day is still the one kind of star ever observed. The first remarkable feature is the light elements from carbon to scandium are displaying a strong odd-even effect, meaning the abundances pattern from this range shows a zigzag pattern where there is relative abundance difference when comparing odd atomic elements and even atomic numbers. This kind of pattern is comparable to the newly discovered star J 1010 plus 2358 formed from a pair instability supernova, which is a special kind of supernova, which will be later explained in detail. The second feature is that the abundances of the light iron peak elements, scandium, titanium, and vanadium, are extremely low. The same abundances were similar to some metal poor stars found in the bulge, halo, and dwarf galaxies. The third, the heavier iron peak elements manganese, nickel, and zinc are quite enhanced, meaning rich in abundance, which similarly matches the spectrum of some extremely metal poor stars associated with hypernova. Finally, fourth, the neutron capture elements from strontium to palladium are highly enhanced similar to stars, for example like HD 1225563, HD 8809. But what makes a difference is the lowest values of barium ever measured, which are found similar to most extreme stars in ultra-faint dwarf galaxies. The most interesting thing is, all of these 4 features have been seen before in individual stars. But it's the first time in history where a star has all of these features together. If we were to add one more feature which is interesting, is that looking into all previously known stars, such extreme abundance features come with a metallicity range of less than -2.5. But this star has a value of -1.76, which is 5 times higher. You might be thinking the numbers are not adding up and don't make sense, right? Well, it is because the whole mathematical equation for finding out metallicity is logarithmic. That's why. The star has a relatively high metallicity and would normally be considered heavily contaminated by general chemical evolution. But the very low abundances of nitrogen, sodium, potassium, scandium, and barium, telling us that it has negligible contamination from general chemical evolution in the interstellar medium. From the analysis of this star, we can be sure that 100% of the sodium and barium came from a swept-up interstellar material, and the rest of the majority of the elements had to be made in one shot, meaning a single nucleosynthesis event or single supernova explosion. If it were a multiple nucleosynthetic event, chances are highly unlikely as production of these elements like sodium, barium, potassium, etc. will be significantly produced and decrease the metallicity of the star, which is not the case as it has relatively high metallicity of -1.76. When it comes to elements from carbon to calcium and neutron capture elements such as uranium, ruthenium found in the star cannot come or produced from a type 1, a supernova. There are different kinds of supernova, but for the sake of time, there is a kind of supernova called type 1a, signifying a thermonuclear explosion of a binary star system where one is a white dwarf and another a companion star, which is typically seen more commonly as a red giant star. What happens is that white dwarf takes the material from the red giant star, creating an accretion disk, and over time the consumption volume rate increases steadily. When the white dwarf mass hit a certain threshold called Chandrasekhar limit, it increases the temperature and pressure of the core, such that different kinds of nuclear fusion reactions takes place simultaneously as a chain reaction to one another, releasing huge amounts of energy, disrupting the white dwarf's outer layers, thrown out to space as a thermonuclear explosion at velocities of thousands of kilometers per second. So coming back to the point, carbon to calcium and post-iron peak elements cannot come out from the Type 1 supernova, instead must be originating from interstellar medium. It seems obvious to ask, but why not a supernova? Well, if it came from that supernova, then it leads to the formation of heavier elements in high abundances, such as nitrogen, sodium, and potassium, which is self-contradicting to the star's whole abundance pattern. In order to create this star precisely, the interstellar medium would need to have one of the highest magnesium, silicon, and calcium abundances ever observed, as well as simultaneously the highest strontium, yttrium, and zirconium abundances known. And it is assumed that only iron peak elements are produced from the Type 1, a supernova. Therefore, from the swept interstellar material, having metallicity of iron around -3.5 is enriched to high metallicity around -1.5 by the Type 1, a supernova. Therefore, we'll have the highest magnesium and strontium abundance ever measured, along with a significant amount of iron too. What's odd about this process is that this Type 1, a supernova, can only be invoked if it occurs within the same region of a galaxy as an extreme core collapse supernova, which means the chance of happening is very rare and seems very unrealistic, and if it were to happen this way, would be an implausible coincidence. Why is this very unlikely? You have these two very different supernovas which are highly unlike to each other, as Type 1, a supernova, and extreme core collapse supernova arise from different progenitor systems and follow different evolutionary pathways. Type 1, a supernova arise from a binary star system having low masses, while extreme core collapse supernova arise from massive stars due to nuclear fuel diminished. The likeness of these two together is very rare. Also, if occurred this way, would produce highest abundances of certain elements, which is contradicting the case for Barbenheimer Star's formation. These statements together make this occurrence solidly implausible. So what could have made this star in the first place? We have some theories, but no one knows for sure, as the latest computational models can't provide the complete formation of this star. This is such a rare and unique star, and that's why we haven't figured it out yet, since the working of the models are based on the known knowledge of these occurrences at a normal scale. We have some compelling theories which are each partially contributing to how this star might have formed. The star's high overall metallicity, low carbon-oxygen ratio, and a strong odd-even effect together prefer progenitors or pre-supernova stars with mass greater than 50 solar masses. However, the whole abundance pattern, especially the iron peak elements, is not fully explained by any existing models of nucleosynthesis in massive stars. There are two possibilities which might explain the star's whole abundance pattern. One source is a hypernova with progenitor mass around 80 solar masses, and the other one is a metal-rich instability supernova progenitor under intermediate processed nucleosynthesis. Intermediate processed nucleosynthesis is the average middle rate of nucleosynthesis in synthesizing heavy elements inside the stellar core. There are other possible contributions to this star's formation. Interaction of different kinds of stars with different kinds of supernovas in a binary star system could be possible, but there isn't in detail research about it. Another possibility of the effect of a nearby black hole or neutron star presence on the formation of this star. Well, stepping all this aside, finally whatever produced the abundant signature of J0931 plus 0038 star, the Barbenheimer Star, was probably very rare. Otherwise, this pattern would probably have already been previously discovered in the thousands of existing metal-poor stellar stars. It's very odd to see that we could explain everything that's going on in the universe. I think we do have pretty good explanations of our massive universe's workings to some extent. But also, I have been watching ourselves as humankind still collecting ocean drops of knowledge for some time now. But there's a whole ocean left to explore and learn about things which we know nothing to be exact right now. You might know this, and the best example is dark matter and energy. But for now, let's leave this to time, hoping in the future we find out answers to all there is and ever will be. Thanks for watching this video. Please like and subscribe to our channel for more new findings and challenging us to think more. Let me know in the comments what you think about it. Thanks for watching, and we'll see you in the next video.